السلام عليكم دكتور، سمعنا؟ سامع دكتور؟ هلو؟ هلو؟
وعليكم السلام ورحمة الله.
سمعنا؟
الشيخ خليفة كيف حالك؟ باهي الله يبارك فيك. تفضل تفضل.
الذكرى نتاع حضرتك مقابلة في الإجازة. كنت لك بدك تعرف أنت فهمني. في الوقت 6 شهور، في الوقت 7، في 8. مرتباتهم نازلة السنة هذه إلى شهر 7.
لا مش هو دكتور هيثم عثمان من الأردن. أوكي. دكتور أحمد حديد. دكتور هيثم عثمان.
سي تيستينج. ايش هو الصوت؟ لا انا هون دكتور. تيست. هلو تيستينج.
دكتورة ليندا. Our first lecture for today is concerning the topic chemical process modeling and simulation and control. We'll begin with Dr. Ahmed Al-Hadid from Germany. As it shows from his biodata, he's a BS student at the Technical University of Munich, specialized in biothermodynamics. His research interests focus on design solvents, Dbitectic solvents and ionic liquids, phase equilibrium in complex systems, as well as molecular modeling and simulation. He will give us a talk about design of Dbitectic solvents, selecting of constituents based on the molecular structure. Dr. Ahmed, you have 15 minutes, please stick to the time, and it's your show. Go ahead, please.
Yeah, thank you very much. Can you hear me well? So, in my presentation, I will talk about the design of Dbitectic solvents and how to select the constituents based on their molecular structure. So, first, what are Dbitectic solvents? Abut and his co-workers found that mixing 1 mole of choline chloride and 2 moles of urea, although the components melt at considerably high temperature, the mixture stays liquid at room temperature. And he introduced the name Dbitectic solvents and defined them as eutectic mixture with a large depression in the melting temperature of the mixture at the eutectic point. So to get information what is or what are eutectic mixture, so we have here a schematic presentation for binary a solid liquid phase diagram, where the components shows complete immiscibility in the solid state, which means that components crystallize as pure components in their stable crystal structure. So the blue lines represent the liquidous lines, which are the temperature at which the last solid disappears, or the melting temperature of this solidus line, or the eutectic line, which represent the temperature at which the first drop of the liquid appears. So as you can see here, when you have a eutectic mixture with a solid state immiscibility, the melting temperature of the mixture is lower than the melting temperature of the both components. And therefore, if we select biodegradable different components that are also green, we can form green solvents with tunable properties. Now, to design Dbitectic solvents, we need to comprehend the solid-liquid phase diagram. Why we need this? Because if we have the solid-liquid phase diagram, we can determine the liquid window. And the liquid window is defined if you have a certain operating temperature, you need the mixture to be liquid below this temperature. And the liquid window is basically the composition range at which your mixture is liquid below the operating temperature. To draw the liquidus lines, or to draw the solid-liquid phase diagram, we use this simple or simplified version of solid-liquid equilibrium condition. And this equation has two main contributions. First, intermolecular interaction, represented by the activity coefficients of the components in the liquid phase, and the pure component melting properties, so melting enthalpy, melting temperature. And keep in mind the simple formula that the melting temperature is just the ratio between melting enthalpy and melting entropy. So to study the effect of intermolecular interaction on the position of the eutectic point, it's clear that if you have negative deviation from ideality, so string intermolecular interactions between unlike molecules in the liquid phase, you have deeper eutectic point or lower eutectic temperature. Also, if you have lower melting enthalpy value of the components, you will have also lower eutectic temperature. Therefore, to design Dbitectic solvents, so eutectic mixture with low eutectic temperature, we need to study the influence of constituent molecular structure on both intermolecular interactions and melting properties. So we start with the melting properties. We have, as we said, melting enthalpy, melting entropy, and melting temperature. Melting temperature is usually available, easy to measure. Now what is left is melting enthalpy and melting entropy. So high melting enthalpy indicates you have strong intermolecular interaction, the crystal lattice. But it's not only depends on the molecular structure, but also it depends on the crystal structure, to give you an idea. So we have here two acids, so Sarcosinic acid, dicarboxylic acid with 2 carbon atoms, and we have here dicarboxylic acid with 3 carbon atoms. And as you can see, the difference in the melting enthalpy is large, although the molecular structure is not so much different, and the functionality, so the interacting groups are the same. And this is due to crystal backing. And see here, you have an efficient crystal backing, and here you have kind of sliding, so inefficient crystal backing. And this considerably affects the melting enthalpy. Therefore, it's very difficult to use group contribution method and to predict the melting enthalpy of molecules based on the molecular structure only. Another really extreme example, sorbitol, mannitol. They have the same number of carbon atoms, the same OH group, but the only difference is just the direction of this OH bond. And you can see clearly that the melting enthalpy is largely different by just the direction of the OH group, and this indicates that it's very difficult to correlate melting enthalpy with molecular structure. Alternatively, we can use the melting entropy, and according to Bondi in the early 90s, he said that the melting entropy is better correlated with molecular structure compared to melting enthalpy. Yalkovsky and his co-workers proposed this simple equation to predict the melting entropy based on molecular structure using rotational entropy and conformational entropy. Rotational entropy can be estimated from rotational symmetry number, which is defined as the number you rotate your molecule and you obtain your original starting structure. And conformational entropy, which can be calculated from flexibility number, and it's simply calculated using this empirical formula where you calculate the number of non-terminal single bond atoms, double bond atoms, and number of ring system in your molecule. So to study this, we studied 6 different eutectic mixture based on menthol mixed with 6 different acids, 3 linear acids and 3 cyclic ones. So the linear acid long chain, so they are more flexible, while cyclic, due to the ring system, they are more rigid. As can you see in the calculated melting entropy, we see a large difference between linear flexible acids and cyclic rigid acids. And this in turn affects the calculating melting, or the calculated eutectic temperature, assuming ideal solution behavior. And as you can see that the eutectic temperature of rigid acids are lower than those of eutectic mixture formed by linear flexible acid, and this was confirmed also experimentally. Therefore, when we want to form Dbitectic solvents, it's always advisable to use rigid or components with rigid molecular structure rather than flexible long chain molecules. Now, for interactions, we modeled the solid-liquid equilibria using the simple 2-suffix Marquardt equation just to see how is the slope or how the activity coefficient depends on the composition of the component. And we have only one binary interaction parameter. So if we have the interaction parameter equal to 0, we have ideal mixture, so we don't have strong intermolecular interaction between unlike molecules. Well, if we have small negative or large negative, binary interaction parameters, this indicates negative deviation from ideal behavior, and in turn indicates strong intermolecular interactions in the liquid solution. For this, we studied choline chloride, very well-known HBA, and we mixed it with 3 different dihydroxybenzene isomers. So it's clear that the one with symmetrical molecular structure, the bara isomer, has the strongest negative deviation, while those of ortho and meta are slightly less. The hydrogen bonding are really smaller compared to that of symmetrical one. Another example, mannitol, sorbitol, as we said, the same number of carbon atoms, the same OH groups, but the only difference on the direction. As can be seen, this rotationally symmetrical mannitol, and this is a rotationally asymmetrical sorbitol, and the difference in the binary interaction parameter or hydrogen bonding in the liquid phase is really large. Yeah? Another really nice example here is sarcosinic acid. So this is rotationally symmetrical. If you add one OH group, you would expect stronger hydrogen bonding, but you see decrease in hydrogen bonding in the liquid phase, and this because you lose the rotational symmetry. If you add another OH group, you again increase the hydrogen bonding because you observe again a rotationally symmetrical molecule. Now, why you have a difference between these two, although you have here additional to OH group? Because of intramolecular hydrogen bonding that can block this OH interacting groups. Yeah. Also a nice example here, we mixed also choline chloride with dicarboxylic acid with in different number of carbon atoms in the chain length. Yeah? So we see here the melting enthalpy, melting temperature, and this is very well known that this zigzag behavior in melting enthalpy and melting temperature of odd-even compounds. So we see here we start with 0, which means we only have 2 dicarboxylic acid groups or oxalic acid. If you add 1 C atom, you increase the melting enthalpy, and this is because in the small acid you have intramolecular hydrogen bonding. Now if you add another C atom, you have even number of carbon atom, you have rotationally symmetrical acid, you have a large melting enthalpy, and then if you add another C atom, you have decrease in the melting enthalpy because you lose rotational symmetry. Again, another even, so you have increased rotational symmetry, higher melting enthalpy, and you have this zigzag behavior. So odd-even behavior. We observe that also in the hydrogen bonding in the liquid phase in the Dbitectic solvents. So if you, again, the 0-1 intrahydrogen bonding, so when you add C atom, you decrease the intramolecular hydrogen bonding, you increase intermolecular hydrogen bonding in the liquid phase. You add another C atom, you have stronger interactions, and then when you add the odd number, you have decrease in interactions, and then again increase when you add another C atom, and then decrease. So the same zigzag behavior in the melting enthalpy is observed also in hydrogen bonding, and this indicates that rotationally symmetrical hydrogen bond donors interact strongly in the liquid phase with hydrogen bond acceptors. So in conclusion, we see that to form Dbitectic solvents, we need strong hydrogen bonding, strong intermolecular interaction between alike molecules in the liquid phase, and we need also low melting enthalpy values. Therefore, to design this with low eutectic temperature, it's always advisable to use rigid molecules that are rotationally symmetrical, such as bara isomers or acids with even number of carbon atoms. However, we should also consider other properties such as viscosity, and we have a nice publication here where we study the influence of molecular structure on the viscosity of Dbitectic solvents. That's it, so thank you very much for your attention. I will be happy to answer your questions.
Okay. We have time for a couple of questions. Yeah, please. Microphone.
I would ask a question, final question, about the last word in your presentation, viscosity. Can you put a correction factor for that viscosity in your...
Sorry, the voice is too low, I can barely hear.
صوت واطي. علي صوتك وقرب الميكروفون, please.
I want to ask you one question about the last word in your presentation. It is about viscosity. Is it possible to put a correction factor for the viscosity to count for its effect?
So your question about viscosity?
Yeah.
And correction factor for it. Again,
you can repeat. Can come here and ask him through this microphone. Much better. Okay, ask.
I would like to ask you a question about viscosity, the last word. I am in an industry that uses a lot of correction factors when there is no modeling or simulation of some important parameters. Can you put a viscosity correction factor for to count for its absence in the model? Thank you.
So you mean modeling of the viscosity. So far we haven't done anything about modeling the viscosity, because when we talk about Dbitectic solvents, your components are solid at room temperature. So you have a liquid mixture at room temperature, but your components are solid at room temperature. Therefore, you don't have the viscosity of pure components. Therefore, normal viscosity models where they account for like correction, as you said, where you just use, for example, a weighted sum of viscosity of the components plus a certain correction factor which represents interactions, for example, or deviation from ideal viscosity. This is not possible because you don't have the viscosity of pure components in the first place. It's something that we are working on now, on how to really extrapolate somehow the viscosity of these of compounds below their melting temperature, but I think it's really a tricky field where a lot of people work on glass. So basically you work with glasses and viscosity of glasses. So yeah, so far we don't have really correct modeling for the viscosity.
Okay, thank you. Any more questions? Yeah.
Can you hear me?
Yeah, this is much better.
Do you hear me?
Yes.
Okay. Yeah, my question is about Eutectic, you know. The word Eutectic, is it, first of all, a property of a component, a property of a mixture? I need more elaboration on this. This is my first question. And the second question is, how the variation of entropy affect the property of being eutectic? Thank you.
Yeah, thank you very much. Really interesting question. I think this is a strong debate in the Dbitectic solvents community. So Dbitectic solvents, by definition, they are mixtures. They are not pure components. They should not be considered as like ionic liquids, where just a pure component. So whatever you do modeling, whatever, for example, you do in process applications, they are mixtures. One of the main problems, for example, if you talk about recycling of this. So, for example, we observe that if you have a DES, you have a binary. So if you have, for example, LLE system where you use one DES and two other solvents as a biphasic system, for example, in CBC or extraction, you don't have ternary system in a sense that you have a DES as a one component, but basically you have a DES as two components, and therefore you have a quaternary system. This increases the complexity when we talk about application of Dbitectic solvents, because they're still considered mixture, not pure components. Therefore, so far we cannot see really industrial application. You can have some assumption. For example, if you have hydrophilic one and you have hydrophobic, you can assume that this will not go to the hydrophobic phase, so they will behave or stay in one phase. So you can consider them as one component, but basically this is not correct, and you most probably will change the ratio when you have some applications, or if you have distillation, you might lose one of the components, and your partitioning of the DES components are different in two phases. So basically they are not pure components, they're still mixture, whether in the liquid phase or in the solid phase. Now, the second question, I think you asked about the entropy. It's very interesting. I think the main understanding for Dbitectic solvent behavior is basically the solid phase, not the liquid phase. Because it's very interesting to see, for example, choline chloride. No matter how they tried in literature, they cannot find any other interesting salt like choline chloride. So choline chloride basically is very special salt, because of its very low melting entropy. If you look at the melting entropy of choline chloride, although it decomposes before melting, but has a solid-solid transition, and the solid-solid transition is almost in the order of magnitude of melting entropy. So what we can say is that entropy changes a lot. Therefore, you can select your components based on molecular structure, because the molecular structure can be correlated to the melting entropy of pure components.
Any more questions? Okay. Can you hear me, please?
Yeah, I can hear you.
Clearly, right?
Can you hear me clearly?
Okay, just a minute, let me introduce you first. It's your turn now. Are you ready?
Yeah, I'm ready.
Yeah, we advanced our schedule because one of our speakers is absent, so...
It's absent, okay.
All right.
Okay.
Dr. Shamsuddin Halado, I'm spelling the name right?
Yeah.
Okay. He's from the Department of Basic Sciences, College of Engineering, Imam Abdurrahman bin Faisal University, Dammam, Saudi Arabia. His PhD in Polymer Synthesis and Applications from King Fahd University of Petroleum and Minerals. He conducted his postdoctoral research on the synthesis of nanomaterials for solar cell applications, as well working as assistant professor of chemistry from the year of 2015 at the Imam Abdurrahman bin Faisal University, Dammam, Saudi Arabia. His research interests focus on polymer synthesis, organelle synthesis, corrosion inhibition, scale inhibition, adsorption, nanomaterials. Dr. Shamsuddin, you have 15 minutes for your talk, so it's your show. Go ahead.
Right. Hello, all the audience. The title of my presentation is a application of RSM modeling to synthetic Gemini Surfactant corrosion inhibition of carbon steel in acidic environment. So this is one of the work we do here to use different corrosion inhibitors and in different environments. So here we just try to see to apply RSM modeling on the corrosion inhibition in order to optimize it. You see, corrosion is actually a big problem faced by many countries globally, and it affects the economy of many countries. So, for example, in the US, it costs about 4 to 5% of GDP, and also many countries have the same problem. So actually, corrosion is a big problem. There are different methods used to control corrosion. One of them is use of corrosion inhibitors. Corrosion inhibitors actually are chemical additives added to the corrosive medium to mitigate the corrosion. For example, in the boilers, maybe during the oil exploration, the oil drilling, these corrosion inhibitors are added to the corrosive medium in order to protect the steel that is used in the casing. Also, as in terms of the mechanism of corrosion inhibition, the corrosion inhibitors actually they form a kind of protective film on the metal surface, and this affects the corrosive medium from affecting the metal. There are various types of organic corrosion inhibitors. Example, the phosphate esters, the quaternary ammonium salts, amidoethyl imidazolines, and the thioglycolic acids. Other natural corrosion inhibitors do exist, such as natural polymers, the plant extracts. Plant extracts actually are now a kind of green corrosion inhibitors because they are non-toxic. As for our work, we selected a model Gemini Surfactant, and I will show the structure later. The Gemini surfactants are kind of surfactants having two hydrophilic head groups that are connected by a spacer, and then a hydrophobic tails. So this is just like a kind of Gemini surfactant. These are the hydrophobic tails, and these are the two hydrophilic groups, and they are usually connected by a spacer. The spacer can be a different chain length, or it can be other groups can be added as the spacers. They have unique properties such as low surface tension, toxicity, low critical micelle concentration, minimal inhibitory concentration, and enhanced water solubility. The cationic inhibitors usually are very good, and they are very efficient in HCl medium due to synergistic effect with the chloride ions. For example, here you can see the surface of the metal is positive in the acidic medium, and the chloride ions are adsorbed to the surface, such that if there is any positive corrosion inhibitor, it can interact with the chloride ions, and the adsorption is very strong. However, sulfate ions in acids such as sulfuric acid, they adsorb weakly on the surface of the metal. Therefore, not all cationic corrosion inhibitors are effective in H2SO4 due to poor absorbability of sulfate ions. So that's how we try to test this Gemini surfactant in 1 molar sulfuric acid, because there are a few number of corrosion inhibitors, cationic corrosion inhibitors that are reported to be very efficient in sulfuric acid. This is the Gemini surfactant we use, and we synthesized it and used it in 1 molar sulfuric acid to test the corrosion inhibition of low carbon steel. And then we applied RSM modeling using based on phase-centered central composite design to see the effect of these parameters, to see the effect of temperature, time, and concentration of the inhibitor. We use a weight loss method or gravimetric experiment. This is in one of the flasks. We add the inhibitor, sulfuric acid, and then in the blank, the inhibitor is not added. It contains only the sulfuric acid. This setup is placed in water bath and kept for a certain time. We change the time to 2 hours, 24 hours, and 48 hours to see the influence of the time and temperature. And then at the end of the time, the coupons are removed, cleaned, and then the corrosion inhibition is calculated, and the corrosion rate also is calculated. These are the operational conditions that were tested, and their level. This is the lower level for the temperature, 25, bit level 45, and high level 65. Exposure time, this is it. And then inhibitor concentration, we use the lowest, 0.01 millimolar. This is the mid level, and this is the higher level. As for these are the responses we considered: weight loss, corrosion rate, and inhibition efficiency, designated as Y1, Y2, and Y3 respectively. These are the experiments we carried out. We performed about 70 runs, and then with the blanks, so about a total of about 50, getting to 50 experiments were carried out. And then these are the operating conditions, and these are the responses. The weight loss is given by Y1, and this is the weight loss obtained after each experiment. This is the corrosion rate, and this is the inhibition efficiency obtained for all the experiments. As for the RSM modeling, the corrosion test data obtained from the central composite design were pitted to the RSM model, the polynomial function given in equation 1, using this software. And then the ANOVA was used to assess and evaluate the quality of the model to determine the correlation between the variables and the significant test. These are to test to evaluate the model's performance. These responses, Y1, Y2, and Y3, the weight loss, the inhibition efficiency, and corrosion rate. To test the quality of RSM model, Y2 coefficient was used to determine using these equations. Now we go to the results and discussions, and these are the best fitted polynomial corrosion inhibition models, Y1 and Y2 and Y3. All the models, they have high values of regression coefficient, and then we also found out that all the single binary and squared terms in the models were all major significant terms in the responses. Therefore, all the terms, the temperature, the time, and the corrosion, the dosage of the inhibitor are very, very important, and they are all significant in the models. So they affect the experimental conditions. And this table, it shows the table here shows the experimental versus the model's RSM predictions. You can see that this is the actual for Y1. This is the actual values, and these are the predicted, and they are very close to each other. You can see even the residual is almost zero. Therefore, the difference between the two is very excellent. This is showing the excellence of the developed models. The models are excellent considering the actual versus the predicted values. As for the ANOVA, this is the table showing the ANOVA for the developed models. It shows that actually there is high quality models are developed for this Gemini Surfactant, and then according to the table, all the requirements such as CV, measures of adequate precision of all the three models, they were all adequately met, showing that the model is well-established model for this process. Then if we go to this is the half normal plot and the Pareto charts for this models. It can be clearly seen that for the weight loss, we can see that the temperature is the major contributor. It is in this order: temperature followed by time, and then inhibitor concentration. But for the Y3, the order is in this one: inhibitor concentration followed by time and then
3 minutes.
temperature. All right. So this can be seen also on the half probability plots. Most of the most influential parameter is away from the line. And these are the three-dimensional plots for these models. And this is the effect of the operation conditions on the weight loss. This is the weight loss, and we can see that the time, it has a positive effect, and the temperature also has a positive effect on the weight loss. As for this one, the temperature has a positive effect, while the inhibitor concentration has a negative effect on the weight loss. And if we go to this plot, we see the inhibitor concentration has a negative effect on the weight loss, and also time has a positive effect on the weight loss. As for the effect of the operation conditions on the corrosion rate, you can see that the time has a positive effect, temperature has also a positive effect, and finally, the effects of the operation conditions on inhibition efficiency. You can see the time has a positive effect, but at a certain time, a kind of leveling effect is observed, and this applies to the inhibition efficiency versus temperature on the effect of the corrosion conditions on these parameters. And finally, conclusively, we investigated the corrosion inhibition performance of the Gemini Surfactant on carbon steel in 1 molar sulfuric acid. The modeling was carried out, and evaluation was carried out and optimized using RSM. The high RSM predictive models were developed for the investigators' responses, and this is the R-square value, and the model fitness is very good. Based on our experiment, the optimal conditions range from 45 degrees Celsius at the temperature, 48 hours, the time, and then the dosage of the inhibitor 0.1 millimolar, and the inhibition efficiency was up to 92%, which is very good, and the weight loss of 0.34, and the corrosion rate was very low, 0.03 millimeter per year. Then it is concluded that RSM can be employed to actually to optimize experiments in corrosion. Thank you very much for your audience. I am ready to take some questions. We are ready.
Thank you, Dr. Shamsuddin. If there is any question, yeah, go ahead.
Thank you for your presentation. I see that your presentation is for modeling with RSM, not for inhibition.
Sorry, I can't hear you.
I see that your presentation is about modeling, not inhibition.
Yeah.
Yes. Can you tell us if the inhibition could be reversed if we use these inhibitors with high velocity erosion, because some inhibitors like amines can reverse inhibition with corrosion if used not logically.
I cannot hear you actually. I cannot hear you fully.
He was asking about the high speed flow. If we can use these inhibitors with the high speed flow that affect the erosion. Can we?
Okay, you mean at high speed?
Yeah.
Yeah, actually, this one, this is static. We carried out this experiment under static conditions, not under dynamic. Sometimes some corrosion inhibitors, many of them at high, when the flow rate is high under dynamic conditions, the efficiency usually decreases. The efficiency decreases. However, in this experiment, we did not consider that one. So this is actually a very good suggestion. Maybe next time we can check the effect of the flow rate. We can use it at different RPM to see how does it affect it, and we can model it. Yeah, this is a very good question. Yeah.
Does that answer?
I hope I answered your question.
Any more questions? Yeah.
Dr. Shamsuddin, first of all, thank you for your fruitful presentation.
Thank you.
I just have an interpretation here. Since you are talking about inhibition, I am expecting here to see a model simulating the temperature effect, the wall thickness effect. Here, really, interesting results that could be implemented in the petrochemical industry, in the mining industry. There you have like a wide variation of the temperature as well a wide variation of different metal types. Here we're talking about a certain kind of metal, a certain concentration and for a certain time. Need to focus more or less on the temperature effect as well on the, if you have like the mechanical rotation of the equipment or the statistical, let's say statistical effects inside, if you're talking about a reactor or let's say a storage tank. Thank you so much.
Thank you very much. Any more questions? Any more communication, contribution? Okay. Thank you, Dr. Shamsuddin.
Okay.
Thank you for your contribution. We are much surprised to have you today.
Okay, thank you.
Do you need to comment about anything?
You say?
Do you need to comment about anything? Do you have anything to say?
Yeah, I just want to say, please, for the for people who want to ask questions, maybe let them try to use a mic that is very clear, because usually it's very difficult to hear the question. Yeah.
Okay. Thank you. Okay, we'll try to do that. Thank you very much. Thank you.
Welcome. Yeah, welcome.
اللي بعديه. Okay. The next speaker will be Azizul Azri bin Mustafa. Are you ready?
Yeah, sure.
Okay.
Let me share my slide first.
Am I pronouncing the name right? Azizul Azri bin Mustafa.
Yeah, it's an Arabic name, so should be correct. Okay.
All right, we have some bio concerning you to share the audience with. Dr. Azizul is currently a senior lecturer at the School of Chemical and Energy Engineering in University Technology, Malaysia. In addition to that, he is also an associate member of the Process Systems Engineering Center at his university, where his research expertise is on physiochemical property modeling and estimation and computer-aided chemical product design. He will talk about solubility modeling of polyphenols in supercritical carbon dioxide and modifier using a cubic plus association model. You have 15 minutes to share with us your lecture, and you can go ahead.
Okay, thank you very much, Mr. Chairman, for the introduction. Assalamu alaikum and a very good day to everybody. So today I'll be sharing our recent work on the solubility modeling of polyphenols in supercritical CO2 and modifier using cubic plus association model. So this is the outline of my presentation, and then for the introduction, so let's start with discussing the polyphenols. So basically polyphenols represents a large and diverse class of compounds present in majority of fruits, herbs and vegetables as secondary plants metabolites. And it is also an important functional food in our nutrition. And the current contribution of polyphenols is focusing on their antioxidative and anti-carcinogenic properties. At present time, several studies and research have been conducted in order to investigate the positive health effects of polyphenols. And today, the demand of polyphenols in the nutraceutical industry has escalated. And for the past 50 years, there are around 1,000 publications related to the isolation and extraction of polyphenols have appeared. And if you look at the figure shown there, so basically there is the US polyphenol demand. So we can see that there is an increase of the demand starting from 2014 up until now, and it is projected to further increase up until 2025 and beyond. Okay, so there are many extraction methods out there to extract polyphenols, and normally conventional methods such as complex extraction method, normally they require longer extraction time, larger amount of solvent as compared to more advanced methods such as microwave assisted, ultrasonic assisted, and also supercritical fluid extraction methods. So the extraction method to be chosen must be fast, eco-friendly, non-toxic, low cost, and also easy to handle. And supercritical fluid extraction, or SFE, have been extensively investigated and also chosen as an alternative in isolation of polyphenols. And it is also one of the widely utilized method due to its clean and environmentally friendly processing technique, even though the process is occurring at high pressure. However, due to limitations in terms of measuring the solubility of the solute experimentally due to time constraint and high cost of experiment, for example, then solubility modeling have been widely considered. It can be developed in many ways. One of it is by fitting it with existing solubility data at different conditions. There are many types of solubility models, which include empirical models, we have kinetic models, we have equational states, which can serve as an alternative to predict behavior and solubilities of solute at different conditions. And it can also be used to optimize separation processes without conducting the real experiments. So in our work, basically we are interested in thermodynamic equation of state model. So basically, Penrobison, PR, and SRK Solvay-Ratliff-Kwong are two of the most widely used and well-known equation of states. However, these two models, they does not account for the strong associating interaction between the polar modifier and also the polar solute polyphenols. So that is why we decide to use the CPA, or cubic plus association modeling, which I will explain in more detail in the next slide. So this is just to highlight the main objective of this current work, which is to develop CPA-based modeling for estimation of the solubility of polyphenols in modifier and supercritical CO2. And in order to support the aforementioned main objective, we have three sub-objectives here, which is the first one is to conduct parameter regression for the binary interaction parameters in this PA model, and number two is to propose a function for the binary interaction parameters in order to increase the application range of the parameter for different temperature and pressure, and finally, of course, to just highlight the applicability of the model in determining optimal condition of an extraction. Here in this case is we are focusing on ferulic acid in SFE. Okay, and so this is the scope of the study. I think I can skip this one. So a bit about the literature review. I just would like to discuss a bit on the SFE. So basically, in SFE, the solute or analyte is extracted from a solid matrix using supercritical fluids, which is a homogeneous fluid, which is a dense gas at a temperature and pressure above the critical points. And one of the most widely used supercritical fluid is CO2, which is a non-polar compound. And so normally the operating condition would be above the critical condition of CO2. Okay, and talking about modifier, so basically in SFE, modifier is optional. It depends on different situation. For example, here in this case, the solid that we are focusing on is polyphenols, which are polar. So, and since CO2 is non-polar, so we need to add a modifier, which is a polar compound, in order to enhance the extraction efficiency of the original solvent. And two of the most widely used modifier is methanol and ethanol. However, methanol is found to be fatal modifier due to its toxicity. Therefore, ethanol have been the better alternative. Okay, so these are some recent published papers on the solubility modeling involving SFE. And if you look at the summary, basically models which have been used include SAF model, PR, and SRK, which provide good result and low deviation from experimental data. However, when looking at these two papers, so basically PR and SRK is not able to provide good results for ternary system because when we have modified, then it will be ternary, and due to its strong interaction that they have between the polar compounds. So, therefore, like I've mentioned before, in this work we are focusing on using a CPA equation of state. So basically, CPA EOS is a combination of the SRK equation of state with the association term in the SAF model. SAF model is another advanced thermodynamic models available out there. So basically, it is trying to taking into account the simplicity of the SRK model equation, which are widely used before. Okay, so in this work, we have described the system using solid vapor equilibrium through this equation. So from this equation, what we can do is that we can predict the solubility of the polyphenols in the extraction. And in order to estimate this value, we need to have several inputs, which include the sublimation pressure, the system pressure, the gas constant, system temperature, and also the molar volume. And finally is the fugacity coefficient. So in order to calculate the pressure of the system, we can use the CPA equation of state. So if you look at this equation, so the first part, the first two expression is representing the SRK equation, and the remaining part is for the association term. And of course, in order to calculate the pressure, there are some more input that need to be included. We have B is the parameter for the core volume, and we have the parameter for the energy parameter, which is A. So since in this system we have a multi-component system, then of course we need to have a certain mixing rules that we need to use in order to calculate these parameters which represent the system. For example, for B, what we need to do first is that we need to find the pure compound parameter, and then we use this mixing rule in order to get the B parameter for the system. So same goes for parameter A. So there are several equations that we need to use, which is involving a mixing rule. And if you look here, in order to calculate the pure compound parameter A, then we need to obtain these parameters A0 and C1. Okay, and then for the mixing rule, we can also see here that we have this Kij. So basically, Kij is the binary interaction parameters, which need to be obtained by through regression with available experimental data. And if you look at the association term, we have this parameter XAI. So in order to obtain this, we need to have to get further parameters, which include this epsilon and beta AIBJ, which is representing the association parameter, energy parameter, and volume. So basically, there are 5 physical parameters which are needed in order to calculate A and B, and also XAI, and finally calculate the pressure. And then finally, what we need is to calculate the fugacity coefficient using these equations. So finally, we should be able to predict the solubility of the polyphenols. Okay, so next is description about the methodology which have been used. So I have the detailed explanation in the next slide, so I will just go directly to the details. So the first stage is focusing on the development of the database for modeling. So we start with, so there are 4 tasks. So first, we start with the selection of polyphenols. So basically, in this work, we are focusing on these 3 polyphenols only, which is ferulic acid, salicylic acid, and cinnamic acid, which falls under the phenolic acid category of polyphenol, because polyphenols consists of many different types of compounds. And for the modifiers, we are only focusing on ethanol. And then task 1.3 is basically the collection of experimental data involving solubility of polyphenols with modifiers, and finally the physical properties of pure components involved. So basically, this is only focusing on development of database, whereby basically we just store all the data in Microsoft Excel. Okay, so stage 2 consists of 2 tasks. So task number 1 is focusing on determination of the type of association scheme for associating components. So in this system, basically we have only three components. We have polyphenols, we have modifier, and also CO2, supercritical. So only 2 of those compounds are associating. And for polyphenols, the for the phenolic acid, it contains the acid groups, and for the modifier, it contains the alcohol groups. So we can use this table to get the association scheme. And then for task 2.2 is basically the determination of the pure component parameters in the modeling, namely A node, C1 and B for the SRK term, and the epsilon and beta A, IBJ for the associating compound. So for the A node, C1 and B parameters, there are two set of equations that can be used, which are divided into whether the compound is non-associating or associating. So if it is a non-associating compound, we can use this equation by Fetohi and Thomson. So basically the input which is needed is the temperature and critical temperature and pressure, the gas constant, and also the omega is the eccentric factor. And for associating compound, there's another set of equations, and for associating compound, there is another two parameters which are needed, which in our case, in this problem, we are obtaining from the literature. Okay, so for stage 3, so after developing the database, after obtaining all the parameters, so what we need to do next is for stage 3, we focus on conducting parameter regression of the KIJ parameters. So here we have provided the index numbers for each of the components. So basically, there are 3 KIJ values that we need to obtain, which is K12, K13, and K23. And this is, like I said just now, we obtain this by fitting it with experimental solubility data. And this is the step. So basically, of course, we start with the inputs, and then we set the CPA equations, and then we set the objective function. So basically, in this stage, the objective is to minimize the difference between the predicted solubility through CPA and with the experimental data. Next, we set the initial gas of the binary parameters and tolerance in the optimization toolbox. And then we calculate the fugacity coefficient, calculate the solubility, and then we check the value with the tolerance. So, of course, if it is not satisfying the tolerance, then of course the value of the KIJ will be updated until it satisfies the tolerance. And so then at the end of the process, we will print out the final value of the KIJ and solubility.
2.5 minutes.
Okay. 1.5 minutes. Okay. All right. So, so just to focus on stage 4. So basically, stage 4 is focusing on developing a function for KIJ, because in stage 3, the KIJ value that we obtain are only focused on certain temperature and pressure. So that's why in stage 4 we focus on developing a function for the KIJ, so that the KIJ can be used for a wider range of for a certain range of temperature and pressure. So basically, if you look at the objective function, we intend to minimize the difference between the KIJ obtained from the function with the previous KIJ value that we obtained from stage 3. So stage 5 basically is just the application, and for the results that we get. So this is the result that we get for stage number 3. Okay, so if you look at this, the results, so the values obtained, the KIJ values are specific. It's very specific for each different combination of temperature and pressure. So that is why we opt for the stage number 4. So before suggesting the function, we look at the behavior of the KIJ that we obtain in stage 3 as compared to the condition of the system. So we find out that for salicylic acid, we get a linear behavior. That's why we use the linear trend, whereby and for the ceramic acid, we found out that there is a second order polynomial trend with temperature, and for ferulic acid, we found out that there is a second order polynomial trend with pressure. So that's why we opt for this function. Okay, and then so these are just some results looking at the trying to validate the results. So this is just comparing the prediction made through the KIJ function and the experimental data. But this is involving training data, which is used in the regression step, and this is comparison between the prediction made using the KIJ function with the test data, data which are not used in the regression step. So we can see that all the data are on the diagonal line, showing that there's a close values between the predicted and the expected data. And this is just to show the result of the application. So basically, based on the KIJ function that we have obtained, so we just we apply it for the extraction of ferroic acid to see what is the optimum condition for the extraction. So this is the optimum condition that we have obtained. And to conclude, so basically in general we can say that CPA with SBE description and using the KIJ function demonstrate a good accuracy to predict the solubility of polyphenols in SFE with modifier, which is ethanol, and represent well the effect of pressure and temperature on solubility and able to determine the optimal condition in SFE. Thank you.
Thank you very much. Thank you very much. We have time for one question, please. Yeah, go ahead.
Hello.
Hi.
I know that equation of states poorly predict the molar volume. How do you account for that?
How do I calculate the molar volume, is it?
Yes.
He's asking that he's saying that the cubic equations are poorly predicting the molar volume. How did you count for that?
Oh, okay. Basically, the molar volume we don't calculate using cubic equation of state. We get it from external equations. I don't specifically remember which equation, but basically we get it from the literature, not using the cubic equation of state.
Okay. Any more questions? Okay, Doctor, as usual, thank you for this fruitful lecture and this contribution. We thank you very much for having you in our conference, and we need to move for the next lecture. Thank you very much.
Right, thank you.
Our next talk will be with Dr. Melloul Sarra from Algeria. Are you ready, sir? The first أول واحد الثاني أيوة. Dr. Melloul, are you ready? موجود هو؟ موجود؟ Okay. Dr. Sarah Melloul, can you hear me? نعم. Please switch on your video so that we can see you. And your mic is off. لازم توديله لأنه ما بسمعني. Sarah, can you hear me? Your pictures flipped. من عندك هاي your picture is flipped. It's upside down. It's okay with us, but it's not okay with you, of course. Can you flip your picture? The camera is flipped, and your mic is off. Yeah. Can you hear me?
Yes.
Okay. Your picture is upside down. Can you turn the camera on the reverse direction?
I don't know how.
This is the problem.
Why is the problem?
Okay, no problem. You can switch off the camera and start your talk. I will need to introduce you first, okay?
Yes.
All right. Sarah, is it Sarah? Sarah Mallour, right?
Yes.
Yeah, okay. Ms. Sarah Mallour is a final year PhD student working on the exploration of local natural plants with respect to the properties and quality of their oil extracts obtained by supercritical carbon dioxide extraction. She is also developing some models to test theoretically different extracting fluids. She is at the Department of Chemical Engineering, Laboratory for Environmental Engineering Process, University of Constantine III, Constantine, Algeria. You have 15 minutes at most, Sarah, to introduce your talk. Go ahead, it's your show.
Assalamu alaikum. Today's presentation I will talk about my research paper on the title of Optimization of Supercritical Carbon Dioxide Extraction of Phenol Designed by Multi-Response Analysis. The objective of this study is to examine the properties of natural plants known as bigamine and mangan. Consider the extraction of phenolic compounds such as phenolic, flavonoids, and tannin from seeds of natural local plants by means of supercritical fluid extraction using carbon dioxide. This plant is widely growing, flowering, highly present in North Africa. Its fame is mainly due to its exceptional composition in alkaloids and their various interesting biological activities. Harman is widely used in traditional Algerian and Maghrebian medicine to treat various disorders, diabetes, rheumatism, and nervous problems, having reduced the tremors, Parkinson's disease. Several studies illustrated different pharmacological activities like antioxidants, antibacterial, antihistaminic, anti-inflammatory properties, and leukemic healing. In addition, it has been reported that this plant has hypoglycemic effect. It is potential source of pigments and essential oils potentially of interest to food, pharmaceutical, and cosmetic industries. The use of medicinal plants in herbal medicine has occupied an important place in biomedical research, which are an important natural source of bioactive molecules, and especially for natural antioxidants. This last one is an important factor for the evaluation of plants of interest in the agri-food and pharmaceutical industrial fields. This property is due to many substances like certain vitamins, flavonoids, polyphenols, etc. So supercritical fluid extraction has been used, which has found wide applications in these industrial fields. It has been introduced as an alternative to conventional extraction technique that require great amounts of solvents that must be eliminated from the extract to avoid harmful consequences on human health and the environment. Different oil extracts obtained by means of the supercritical carbon dioxide extraction are shown in the present figures. It can be seen that these extracts show two distinct phases of different color and amounts depending on the set operating conditions. This can be regarded as a very important result since the operating parameters can be manipulated according to the desired extract composition and extraction yield. The extraction yield, total phenolic compound, flavonoid, tannin, and inhibition concentration were optimized and the corresponding operation conditions were determined. A box bank and statistical design was used to investigate the effects of operating parameters like pressure, temperature, and particle size at fixed supercritical carbon dioxide for an extraction time of 3 hours. Using the experimentally measured oil extraction yield values, a second order polynomial relationship between the response and the independent variables, particle size, temperature, and pressure was obtained by multiple linear regressions using minitab and expressed as follows. This table of C shows that the polynomial regression model was in good agreement with the experimental results, which with coefficient of determination value were 98, 97, 95, 90 respectively, and adjusted coefficient of determination were 94, 92, 86, 72 respectively. The results of the extraction carried out by carbon dioxide are also summarized in these figures. And this results a positive pressure effect on the extraction yield was observed, since increasing the pressure would increase the density of the fluid, that is, mean increase of the solvent's power, and the better oil solubility in solvents, hence accelerate the rise of mass transfer and diffusion of the solvent into the system, and improve the extraction performance. Figure 2 shows a linear evolution of the extraction speed by increasing the pressure, as we see at constant temperature and, for example, at 100 bar. The extraction was slower and the extract yield was almost constant over the extraction time. While at higher pressure, 300 bar, the maximum extracted mass was mainly during the first 20 minutes. A priori, it can then be concluded that by increasing the extraction pressure, a better efficiency of the solvent is obtained. Also, for the temperature condition test, two effects can be observed, opposite and an opposite effects. When the pressure drops below, for example, 150 bar, the temperature has an opposite effect on the oil, confirming the general trend reported in the literature, where a temperature increase leads to a decrease of the extraction efficiency. Also, for the particle size, the highest yield obtained for low mean particle size 0.3. We observe that the extraction yield increase with decreasing particle size due to the fact that the cleaning process increases the transfer area, decrease the intra-particle diffusion resistance, and release oil from the broken cells. In addition, Figure 3 shows qualitatively a good agreement between the total phenolic compound and the
It looks that we We lost the connection with Miss Sarah, so we'll just wait for a minute. نستنى شوية بس. If she can restore her connection, and then we continue. Sarah, are you there? Yeah? مرة ها؟ Okay, I think خلاص ها؟ Unfortunately, we lost the connection with Miss Sarah Melloul, so she cannot complete her lecture, and then we will not have the opportunity for contributing to her communication concerning having some questions to be answered by her. So, all right, I think we'll wrap it for the first part of our session for today, and I need to invite all of you for a short coffee break. Then we'll come back again to continue with the
afternoon. First of all, I would like to apologize for this or the technical failure with the presentation. Again, I would like to thank Mr. Chairman for the introduction. Today I'm going to introduce you my topic about theoretical simulation on the best topology for desulfurization of crude oil. Next slide. Next slide. First of all, I'm going to start with the state of the art in regarding this desulfurization process. Next. Potential substitutes for traditional fossil fuels such as shale oil or heavy oil are mainly characterized by complex and long hydrocarbon chains. These containing recalcitrant elements such as organic sulfur components or derivatives. These derivatives have the weight percent of more than 8%. Next. Desulfurization, or let's call refinement. Desulfurization, or what's called desulfurization, or what's called the immobilization of organic sulfur derivatives, mainly to remove, let's say, sulfur content from the crude oil derivatives and to meet what's called the international specification. These international specifications are summarized or characterized by the symbol ULSD, ultra-low sulfide distillate, which is lower than the 15 ppm. Conventional hydro-treating desulfurization process, HDS, the process which is running in the industry for the current industrial applications, is visible only under prevailing conditions. This means that we need high temperature, high pressure, and massive amount of hydrogen, the expensive hydrogen, besides to the expensive catalyst. Next. HDS is crisp. This means that weak for treating crude oil with higher sulfur content of the more than 8%. The non-hydrotreating processes, such as the catalytic oxidative desulfurization, named by ODS, and direct desulfurization. There are techniques already exist, but not, let's say, industrially, let's say, commercialized are not yet industrially commercialized. Thank you. Yalla, Dr. Shukran. Next, I'm going to show the block diagram for HDS, traditional TRDS. Here, we see in yellow, it's the catalytic hydro desulphurization process. We have the high sulfur influence is getting to this process. In this process, we are going to introduce the hydrogen, this hydrogen, and the reaction is taking place after a certain retention time. And the ingredients from the reaction are going to be separated. The unreacted hydrogen is retained or routed upstream, let's say the reaction or the HDS process, and the distillate are routed downstream to the what's called the sulfur content middle distillate separation, going to separate between the low sulfur and the high sulfur. The low sulfur is our product, and the let's say the high sulfur, or let's say this stream, which was called more or less, it is what is hydrocarbon loss. This process this process, as I told you before, it's crisp, meal or less. For higher sulfur to hydrocarbon ratio, we need high temperature and high pressure, as well the massive amount of hydrogen. Next, I'm going to describe what's called the standalone desulphurization or direct desulphurization. In the standalone direct desulphurization, we have as well the block diagram show you. Here, the high sulfur content, the direct desulphurization, the main process will be shown on the next slide. Then, coming the separation process between the product and the high sulfur content. These أصابت عنده؟ Yeah. Yeah. Oh, it's back. Now we're going to talk about the virtues of standalone desulphurization process. There are many other processes in the industry regarding the desulphurization process, what's called the adsorptive ADS process. This process has the advantages, disadvantages. Main advantages, it is a physical or a chemical, let's say, there could be physical or chemical adsorption performed on a solid surface. Solvent, dealing with solid solvent is more or less is simple process. Disadvantages, here, downstream regeneration and higher retention times are foreseen. Next. The other techniques are existing, like for the standalone is the extractive EDS using ion liquids, ILS. These techniques depends on the polarity of the organ-sulfur compounds, which enhances the selectivity of the ILS. But the disadvantages are approachments of solubility. This means that of sulfur content as well hydrocarbon, they have more or less similarity in the polarity, and they will be selectively separated. Next. There is what's called the catalytic alkenation and Eutectic. This new technique mainly applied in the UK, shifting the boiling temperature of organic sulfur compounds, cracking of the long chain, and the cyclic S content derivatives. This means that the distillation process is required downstream this process. The only disadvantage of this process is that it's selective to only thiophene compounds in olefins, long chain olefins. Next. Some other techniques is what's called the biodesulfurization. The biodesulfurization in BOD. Here, as you see that we are applying enzymic or what's called the biocatalyst. And these biocatalysts depends on batch process and a relatively long retention time are foreseen. Next. Now to the next process or to the next challenge is what's the combination of EDS and ODS and EDS process. Next. Next. Here you see the block diagram for the 5 main streams, the sulfur as well as the oxidant, then coming to the, let's say the reaction stage, coming to the oxidant separation, the oxidant or the unspent oxidant is getting back to the upstream catalytic process, the downstream here getting, we are introducing the extractor or extractant to separate between the two, let's say derivatives, the low sulfur and the high sulfur derivatives. Next. Now, our investigations involve 3 kinds of oxidants. We have the gaseous oxidant, oxygen, next, as well H2O or hydrogen peroxide in aqueous medium of sulfuric acid solution with volume ratio 1:1, and the next is the hydrogen peroxide in organic, let's say citric acid with 1:1 ratio. Next. The boundary conditions, I'm going to show the feed that we are work with. Here you see the 3 different influence. The 3 different influence, they are the mainly or to cover, let's say the fraction for benzene and diesel and the crude oil. But you see that the sulfur content is varied between 3 weight%, 7 weight%, and the 10 weight%. Why these numbers? The 3 is the traditional, which is carried out in the let's say in the current, or let's say in the current investigations. The 7, which is coming from the shale oil, and the 10%, it is, let's say, the extreme let's say limit, which is coming from the heavy oil or from the shale oil. Next, please. Now going to the results. Next. Yeah. For the 3 weight% with HDS process, you will see here in our table, let's say the mass diagram. Next. The mass diagram here, you will see the 5, let's say the 5 streams. Boundary condition, you're talking about something like 4.4 megapascal. This is the high temperature and the high pressure that we need for this process. The feed flow rate is similar, 1,000 kilogram per hour. And you see that we have the loss, which is about 29.5%. It is with respect to the feed stream as a hydrocarbon loss. Now, by increasing the, for the next feed, 7 weight%, we have the same results, but you see that the losses, which is exceeding or approaching the middle, or let's say 50%. Even in 10%, 10 weight%, we are reaching about, yeah, we are exceeding this. This means that this is a hydrocarbon loss that we have to deal with it in industry. Next, please. The results now, the results with the oxidant number 1 is with oxygen, with the gaseous oxygen, 3 for the 3 weight%. Here we are talking about like mild condition according to the literature. This means that the mild condition talking about a pressure of 200 kilopascal, 2 bars, and a temperature of about 70, which is above the room temperature, below the boiling point of water. Here we are approaching the hydrocarbon loss of about 186 kilogram per hour. Next. For the 7 weight%, the same results, but we are approaching the 23% for the feed gas, the feed crude oil, and for the 10%, we are approaching the 41%. This means that these numbers referring to the hydrocarbon loss with the gaseous oxygen, which is the main or the first step for improving this process. We have the same results now to show with the next oxidant, please. The next oxidant number 2, it is the gas or the hydrogen peroxide in a sulfuric acid with 1:1 ratio. Yeah, next please. Next. As you see here that the hydrocarbon loss regarding to the phase or the gaseous oxygen, we have even a lower number, approaching the lower numbers. Why is this? Why is the approaching for the hydrogen peroxide better, hydrogen peroxide in sulfuric acid better than oxygen, or even if you're going to go further with the organic acid, we even have better performance for the ODS-EDS process. Here with the option number 3, with the hydrogen peroxide in organic or sulfuric acid, we are approaching or almost approaching a good performance. For 10% we have almost 12.8 hydrocarbon loss. This result is can be attributed to the effect of the let's say the polarity. As you see that we have explained before that the extractive process depends on the polarity. The acetic acid decreasing the polarity. This means that similarity between the hydrocarbon and the S derivatives is not more the same. So it could be easily separated. This is this means that using oxidant in organic acid, the hydrogen peroxide is better than the hydrogen, with aqueous sulfuric acid. Here's let's say for the process design, it's very important table. We are using it as a process designer. For the removal, you see that the 3 challenges here, moderate, we are achieving by the ODS as better as removal. The operating conditions sophisticated, even because of the higher temperature and higher pressure. For the plant availability, in the case of the HDS, it's low because you are using compressors, rotary equipment, having much problems or zero problems that could cause the shutdown of the process. Latency, it is the retention time. We need more or less in the EDX, it's high. You have to wait some long times. Waste management, because of in the case of the HDS, we have the high value because we are producing H2S, which is a harmful gas for the industry or for the environment. For the capex, depending on these operating conditions, we have estimated the capex. In the case of the HDS, they are high, but we are getting lower capex in the case of the ODS-EDS process, and even in the OPEX, they are like 60% of the HDS of the OPEX in case of HDS. Finally, coming to the conclusion, a new topology was developed to establish the target LULSD limit. Oh, getting back, please. Coupling. This is the process, coupling ODS with the EDS process is dependable and cost competitive topology for sulfur deimmobilization, or let's say immobilization, convenience of H2O2 in organic acidic medium as an oxidant for ODS, and in high selective ionic liquids for EDS promote better as immobilization from crude oil. Organic sulfur deposits are subject for further, let's say, treatment to recover this valuable sulfur compound. Last but not least, next. Coming to the end of my presentation, again, thank you for your attention and for your patience, and your questions are welcome.
Thank you very much, Dr. Saad, and sorry for the inconvenience at the commencement of your lecture. Any questions?
Mr. Chairman?
Yes.
Hello?
Oh, yeah. Raise your hand.
Yeah. Hello?
Yeah, go ahead.
Please, I'm Wajdi Ratemi. I don't know. I'm scheduled at 15:50. So
I know we are sorry.
Yes.
We are sorry for the delay because there are certain things happened during the scheduling of the lectures, but you are scheduled for the
I thought because the session was ended by the host, I thought something.
No. We're still on.
I thought it was
we're still on.
Reorganized. Okay. Good. Thank you.
Yeah. Any questions, please? Any questions? Okay. Thank you, Dr. Saad, for your valuable contribution, and we will move into our next presenter, Mariam Boterra from Algeria. Is she ready? Mariam? موجودة؟ مريم. No, she's not there. Ms. Mariam? Okay. Our next presenter is Siti Aslina Hussein from Malaysia.
Yes, I'm here.
Okay. الصوت من عندك.
Can you disable the screen sharing? I want to share my...
Okay. تسوي sharing.
Can you please disable?
Just a minute. Just a minute. We are trying to fix the...
Okay.
Yeah. كانت قبل شوي معنا. Dr. Aslina, do you hear me?
Yes.
Okay. Is your video camera switch off? Your video camera is switched off. Okay.
Yes.
We can see you now. All right, that's it? Okay, let me first introduce you, then we can start. All right, our next talk is about population balance modeling for characteristic bubble breakup and collisionous dispersions, which will be presented by Dr. Siti Aslina Hussein. Did I pronounce the name right? The name is correct.
I cannot hear, Mr. Chairman.
Okay. You cannot hear me? Can you hear me now?
Yeah, but I cannot. Yes, I can hear now.
Can you hear me now?
Yes, yes.
Clearly, okay?
Yes.
All right. Let me present you first. Our next talk will be presented by Dr. Siti Aslina Hussein. She will talk about population balance modeling for characteristic of bubble breakup and collisionous dispersions. She worked at the University, Porta, Malaysia, Department of Chemical and Environmental Engineering, and she worked there for more than 20 years. Her expertise in research included multi-phase flow, chemical process and engineering, simulation, and process safety and loss prevention. You have 15 minutes, Doctor, so you can start now.
Okay, thank you so much, but I can't share my slide.
Yeah.
The host is disabled for me to share.
You can share now.
I can share now, okay. Stop. Wait.
تمام. You have to make share screen.
Where have share? I don't see my file. Share screen. Wait. Files. How to share? Where to put my file?
Just
Press on share screen, then you check on your file where
you can start on your presentation and then click on the share screen.
Yeah, I share screen, but my files is not in. Wait, Okay, wait. I transfer my files. Share screen. Oops. Why I can't share? File and folder.
You are given, okay, yes.
I cannot share. I supposed to share screen, and then there is a few Google Drive, Microsoft OneDrive.
Should look for your file and open it.
Yeah, I can't get it. My file here. I don't know why. Dropbox. Security. Oh, okay. Security.
The problem is to find your file. It's by your side there.
I think there is a security that locked me. I cannot share.
You are given the permission to share, so the privilege is there.
What's this?
Just start your presentation and click share screen. Did you start your presentation at your computer?
I don't know why I cannot share. Dropbox, security and privacy. Security and privacy. I'm so sorry. I tried to.
I can switch to the next presenter and we can delay yours after the next one. Can we do that till you find?
Oh yes, I can do this now. Wait,
شوف الدكتور تيمي، الدكتور الثاني اللي بعديها موجود هو. دكتور وجدي موجود؟ دكتور وجدي. دكتور وجدي موجود؟ دكتور وجدي انزل تحت شوي بالله، شوف انزل تحت شوي. وين راح؟ هو كان موجود قبل شوي. دكتور وجدي موجود؟ دكتور وجدي your mic is off. سامعني؟
السلام عليكم.
عليكم. الدكتور وجدي بسبب صعوبات
قاعد الاخر عبد المجيد. لحظه بس يا دكتور لو سمحتوا. قاعد عبد المجيد يقول لي يجيب بس الدوكمنت ما بس يطلع. شوية يا دكتور لحظة بس.
Okay, go ahead.
أنا أنا بندير عندي شير سكرين هذه، أوكي؟ فلما بندير الشير المفروض تطلع هذه اللي بندير الشير هذي. نفس المشكلة هي دكتور اللي لحظة بس.
Yes.
لما ندير هي كذا شير سكرين هذه، فهمت؟ معناه المفروض نبي نطلع فيه دوكيومنتس على الديسك توب يعني. هي اللي بنعرضها. وين هذه؟ فايلز ها؟ لكن المفروض على الديسك توب. هيك عم نزيد يظبطها أكثر. لا خليها ببالك شير ساوند ولا؟ فيش هذا المفروض عادي يطلع لك الدايركت وتمشي تاخذه. لا تاخذه من برا. هي المفروض ظابطينها ولا؟
مشاكل عنده.
هو في لكم تبي تحطوه هو هذا في الواحد البرزنتيشن بتاعي لما نديرها شير تطلع لهم حتى هم. تقريبا عند مجيد يظبطها بالله يضبح عليك. لحظة بس يا دكتور بين على the same problem اللي with Dr. City I also experience. I have to sometime just to at least to manage how to get the file. Unfortunate. Should you disable your sharing screen yourself there?
No, we enable the sharing for you. So.
Yeah, I do, but the panels that opens doesn't show my documents. I can show you. I show you what I see here.
Do you have the sharing enabled by your side?
Oh, okay. Just a second. Okay. I have to click. Okay. I think maybe I'll.
You were given the privilege of sharing, so.
Yeah, I think, okay, now I didn't click on the share, so now I hope it will open it.
Oh, something is coming there.
Yeah, I think so. Okay.
Yeah, okay.
Maybe the lady, the same thing for Dr. City, she when she opens, she should click on the share, so
this is what I told her.
It will open her documents also.
Let me introduce you
first,
and
so I will start.
Just a minute. Let me introduce you first,
please.
Also, due to technical difficulties, we have to switch the talks between Dr. Wajdi and Dr. Siti. Dr. Wajdi Muhammad Ratimi from University of Tripoli. He's gained his BSc in 1977, MSc in Nuclear Engineering from University of Wisconsin, Madison, USA. His Doctor of Engineering from Kyoto University, Japan. Currently is a full professor at the Nuclear Engineering Department, University of Tripoli. His research interests in modeling, simulation, control of nuclear reactors and power plants, as well as in artificial intelligence, probability, and number theory. You will be given 15 minutes, Dr. Wajdi.
Please, so will you open access for me to record my presentation, please?
It is already recorded. It's being recorded.
Okay. Yeah. Okay. Yeah. Thank you, sir.
Go ahead.
I'm very happy to work with you in this very nice conference, and thank you for inviting me to give this presentation. And although my field is nuclear,
switch on your camera, Dr. Wajdi. We need to see your. Okay.
Okay. So as I said, although I am a nuclear engineer, but my talk today will be presented mostly based on some mathematics and access to modeling, and maybe other extended informations that can be accessed and used by other disciplines. And I would recommend also chemical engineering and chemical science, maybe they can make use for this. Okay, I think my name is Wajdi Ratem. I'm professor at the Nuclear Engineering Department, University of Tripoli, Libya. And my talk will be concentrated on those items. I just mentioned the purpose of the contributions in this conference. As I said, maybe exchange of knowledge from different fields could help different fields to access knowledge from field to the other. Although, as I said, it's not purely directed towards chemical science and chemical engineering. The second point that I will discuss is I will talk about research at a glance, or the trigger for my research, which I will be presenting today. Two basic lines I will talk about: revisited nuclear reactor kinetics, and also revisited Pascal Triangle, which is a very well-known triangle. Also, then I will highlight some applications and then conclusion. Regarding research at a glance, two parts I will be talking in this presentation, mostly about nuclear reactor kinetics. We revisited it. That means we have, as we can see, we have a classical reactor kinetics that models the nuclear reactors. And basically, from the kinetic point of view, there we can describe nuclear reactors in terms of 7 coupled first-order differential equations and the corresponding characteristic equations, which is, we call it the in-hour equation. In my talk, as I said, for the expansions of this in-hour equations that I highlight here, I assigned it as a homework to my students in 1996, I think. And when I expected the result, there were about 7 pages of the expansion. So I asked the question, is there a way that we can reduce those 7 pages to a very small equations? And so it did. We tried to work on this problem, and we had to devise this tool. This is the trigger for the expansions that we used to expand in our equation. The result resulted in a model. We call it a coefficients-based model for the nuclear reactor kinetics, with the corresponding characteristic equations, which is a polynomial in our equations. The coefficients AMs are made of what we call universal ABC values, and those universal ABC values, they are used from standard constants for the reactor related to delayed neutron fractions and decay constants, and we call them universal ABC values because they depend on the type of the fuel of the reactor, and once we choose the type of the fuel, then those universal ABC values are constant. So we will highlight on this. The second part will be the Pascal Triangle. Pascal Triangle that we all know by the name of the Pascal. Actually, it started from the 5th century by what we call staircase mount mirror, developed by Haliuda. Then Umar al-Khayyam triangle in the 11th century. In the 13th century, Yang Hu triangle. A Chinese developed in the same triangle. And in the 17th century, Pascal revisited the Yang Hu, and he developed the well-known Pascal Triangle, and he used it also for probability and binomial expansion. In the 21st century, we extended this binomial coefficients, which is x plus y to the power n, to be x plus y plus z plus w plus I up to whatever variable raised to the power n. And in that respect, we generated what we call a generalized Pascal triangle. So to start with the nuclear reactor kinetics revisited, as I said, this is in our equation. We ask it to expand, and as I said, the coefficients for this expansions developed into 6 to 7 pages for complicated descriptions, combinations of lambdas and betas, depending on the number n here for the group. We only developed for 6 groups and developed the 6 pages. If we have more groups, then that will be more rigorous. The idea was to expand this, and we noticed that we have this term here, W plus lambda I, multiplied n times, and this is the way we wanted to develop some mathematical tool to expand this term, and this is the formula we developed, and we called it later on Guelph Expansion. The summations of lambdas combinations of K denotes the sum of the product of each and every possible combinations of K elements of the set lambda 1 up to lambda n. The number of such combinations is in fact the binomial coefficients known as Nk, which is n factorial over K factorial over n minus K factorial. So expanding this, and we can find that the terms, as we can see here, the pi of omega plus lambda i's multiplied n times and so forth for the other terms, and this is it has to be expanded, and we use the formula as shown here, and ultimately we developed in our polynomial in a very simple form given by this summation am omega to the power m equal to 0. And the coefficients AMs are given by this formula. So this is the equations, and this is the result of the AMs. Once we expand this, this is what will present the 7 or 6 pages of the expansions. But as this presented by 2 lines, we can computerize this and make an algorithm to generate all the coefficients needed. The model developed there is this. This is the characteristic equations of the model, and this is the new form of the nuclear reactor kinetics model, which is a single nth order differential equations compared to nth first order coupled first order differential equation. Next. These are the AMs, as I mentioned, and this is another compact form for them, which represents the universal ABC values, AM, BM, CM. We calculated this for uranium-235 fuel, and the generated coefficients are given in this table, and the new form of in our polynomial, which is different from the available classical in our equations available in the literature, and this is the new form where this represents insertion for negative reactivity. That means we put all the control rods of the reactor inside the reactor, and all the roots will be in the negative side, and this is for positive insertion of reactivity. That means we raise the nuclear control rods from the reactor, and there will be one positive root and the rest will be the negative roots. The next part, which is the Pascal Triangle, this is a very interesting part. There's a video developed by the TED, Education TED, and I contributed in this video. You can connect to it and see it later if you are interested. It talks about the secrets of Pascal Triangle and its extension to the new part of generalized Pascal Triangle. So the ideas of the generalization of Pascal Triangle starts again from the same trigger that we started with, the expansions of the omega plus lambda i's multiplied n times with this devised mathematical tool representing this expansion. If we consider lambda i's as a single lambda, then it will be transformed to this form. In XY notation, this represents a binomial coefficient expansion. This is a binomial coefficient expansion generated from the expansion developed here.
2 minutes.
Okay, this then generation of NKs, this is the Pascal triangle generated, the regular. We extended this to multi-elements, X, Y, Z plus W, R, S to the power N, and the expansion shows in this form. This is one way to generate the coefficients. As we can see, the red lines, the red are the classical Pascal triangle, and the other steps represents the expansions of the multinomial. This is a trinomial, and this is quadrinomial. And the idea for the embedded Pascal triangle, we put the classical Pascal triangle vertically, then we lay out horizontally Pascal triangle elements, and we make the multiplications, and we can generate the multinomial expansion. Another way to generate the method, we called it the staircase horizontal vertical method. We start with one, then we make one step, and we put this one in the first step, then we multiply it by the columns of W1. The W1 is set of this, all the terms R1. Then we take one steps, staircase in one steps, and we extend all those ones under the steps. Then each step we multiply by W1, W2, W3, W, the columns of this matrix. This will generate the X plus Y. If we take the expansion here, 1, 1, 1, and we make steps 1, 1, 1, 1 to 1, the third step, then 1, 3, 3, 3, 1, another step with the elements 1, 3, 3, 1, and another step with the elements 1, 4, 6, 4, 1 of the previous triangle. Then we multiply each step by the columns of W1, W2, W3. We generate the X plus YZ. We take the same processes to generate X plus Y plus Z plus N plus W and so forth. So this is applications for such idea. We can use the binomial expansion for coin tossing. If we had head and tails, then we can calculate the probabilities for the types. Also, we can extend it to dice tossing. We can extend it to study of minimal cut sets for fault tree analysis. We can extend the study for multivariables for like neutron life cycle, combinatorics. If you have 5 boys and you want the probability of having 3 girls and 2 boys, then you can generate it from this binomial expansion and multinomial expansion. Also, we can extend into DNA sequencing for the variable A, T, C, G, just like XY plus XY, Z, W. Then we can calculate the probability of having all the string of the DNA, all A, the 4 of them, and this is its a probability. If we have 3 A's and 1 C, and this is the probability, and so forth. Of course, the idea can be extended to other disciplines, chemical science, and engineering could be one of them. So maybe who are interested in this type of extended Pascal triangle could find a use for it in the chemical engineering. In conclusions, in this talk, I tried to present a polynomial expansion tool to serve for compacting long expansion. The application of this tool, named as the Guelph Expansion, leads to presentation of a new form of nuclear reactor kinetics. It turns out that a special form of the Guelph expansion represents a binomial expansion. The coefficients of which are called the binomial coefficients, and they represents the famous Pascal triangle. We showed an extension of this Pascal triangle for a binomial to a generalized Pascal triangle that takes multinomial expansion. Different applications were highlighted, and the research is open for further explorations in other fields and disciplines. Chemical science and engineering can be one of them. Thank you very much for your attention.
Thank you very much,
Sorry if
if there's anyone have a question for Dr. Ratimi? I have one myself.
Please, if you raise your voice, because I barely hear you.
Okay, do you hear me now?
Oh, okay, now okay.
Okay, I have one question for you. What kind of chemical engineering application that this method might serve it in terms of modeling?
This is the challenge, because the point is that the idea started to expand this Pascal triangle to generalization. Then by research I tried to apply it to my area and in nuclear engineering. So I would think that maybe the specialized people in chemical engineering could find a way to apply it, and that's why I made it as a challenge that the idea can be presented in many fields. As we said, maybe for genomics studies, you can find an application.
I think so.
For combinatorics, you can find application.
Exactly.
I'm sure that chemical engineers can find a way to find a solution for this.
Thank you very much for this valuable contribution. And I need to move to our last speaker, Dr. Seti. Thank you, Dr. Ratimi. Yeah.
Let me share the screen. Can you all pass the screen to me?
نعم.
Dr. my side.
Dr. Ratimi, thank you very much for your contribution. My mic was off, in fact. Can you stop your presentation? تقدر توقف من عندك أنت.
How to stop it? Okay.
Yeah.
I will leave. I will leave.
Yes. Okay. You should start your presentation and then make the sharing. Okay.
Wait, huh? Can you see the screen?
Yes. Doctor, no. Dr. Hussein, you are the last speaker for today, so I wish you can wrap it up in the shortest time possible. So you have 10 to 15 minutes, please.
Okay, wait, huh?
Go ahead.
Okay, Assalamualaikum and good afternoon. Good afternoon. I'm so sorry for the delay for me, and thank you so much to the chairperson and also other panelists. And today I would like to present the title Population Balance Modeling for Characteristic of Bubble Breakup and Condensers Dispersion. And I'm Dr. Siti Asina Hussein from Faculty of Engineering, Musti Putra, Malaysia. So let me introduce from our side. I'm from Faculty of Engineering, as you can see there. This is our faculty that established since 1975. So it's actually located in Serdang, Selangor, about 20 kilometers from KLCC, the Twin Tower. If you want to come, please welcome and visit University Putra Malaysia, whereby you can have a look at the Twin Tower in Kuala Lumpur. Right. As you can see here, the presentation outline, of course, from the introduction, methodology, result and discussion, and also the conclusion. Okay, the industry, in general, the world industry utilize the bubble column reactor as part of the process method nowadays, such as you can see the first picture, is a chemical industry plant, the petrochemicals, bioprocessing, and also the pharmaceuticals. So if you see there, this is a picture showing the bubble column reactor. It's a common reactor that being used as a concept, very simple concept for the gas phase distributed into the fluid continuous phase in form of bubbles. And okay, so basic introduction on the bubble column, we have the gas inlet and the gas outlet. Then we have a sparger here with a liquid pool. So the liquid pool sparger by a process stream. So the gas inlet will be flow vertically towards up of the reactor. So it's actually widely used in chemical, petrochemicals, and other industry nowadays. So why? Because of the operation. No mechanical operation is a good mass and heat transfer. But in a way, what is the issue of the design, especially? For example, the parameters that have in the design issues, gas hold up, dispersion, axial dispersion, the mixing time, the flow rate, the resident time, and also the flow region transition. So as we can see here, is very a simple mechanical operation from the inlet at bottom to the outlet at the top. And why the issue for the gas for the bubble column reactor is the most important thing is the gas hold up. Why? Because it's the key parameter for design aspect for the calculation, such as previous research work done by Katarsi et al. Okay, so as you can see here, figure 2 showing how is the gas hold up and the flow region transition between homogeneous flow to the transition. You can see from bottom to the top. Okay, so from this view, we can see why we want to investigate on this reactor, because every time the experimental work or the research work that have been done, we can't get the exactly value or data taken. Okay, so this is why, because influenced by the gas velocity, the sparger design, liquid properties, and also the temperature and pressure operating. Okay, so in our research investigation, for these particular articles and the research project, I'm focusing on the simulation that we are being used, ANSYS computational fluid dynamic with the ANSYS software code music model. Okay, why music model? Because the model combine a population balance method for size distribution with the CFD analysis. Okay, so this size distribution, why? Because we want to see at that particular area what is the size that a group of size. Yeah, we want to see a group of size distribute across the vertical reactor. So this size range of the bubble is split into several groups. Okay, so as you can see here, there are few groups of bubbles size that they are solved by solving in terms of mass fraction. Okay, so two-phase flow calculation can be extended to include equation for the mass fraction of bubble within the several size ranges using the music model. Okay, so the music model is actually already in the CFX equation and also the software. So it's already in. We just like set up the groups of the bubbles and run the simulation. We want to see what will happen to the distribution across the vertical reactor.
You are short on time, Dr. Sethi, so I have to speed up.
Oh, okay, so this is part of the introduction, previous work. Okay, I speed up. So the objective is to incorporate the population balance model in simulation with appropriate modeling of coalescence and breakup. We want to see how is the size of bubble that can change to due to coalescence and the breakup process in gas liquid bubbles. Okay, so this is where we have the experimental work. We have the schematic diagram of bubble column, the Sparger design 0.2 times 0.2 with 361 holes, number of holes. The diameter of holes is 0.5. So we only take superficial gas velocity with 0.125 and 0.0627. Right, so this is the experimental work, and this is the mesh that we create from the geometry model with the parameter and the condition taken as in the table. Okay, so the result showing that the comparison of average bubble size distribution is significantly agree with less than 6%, less than 6%, okay? So this is a comparison between experimental work and the simulation. So this blue dot is showing a group of bubble size distribution across the vertical reactor. And this is the other flow rate that superficial velocity that have been used. So, and this is to show what will happen to the bubbles size across the surface radials. Okay, so if you can see here, the lower the actual liquid velocity, meaning that the bubble size, the bubble size is smaller. So we want the bubble size smaller because we want to have the homogeneous and dispersion bubble stream, bubble regime. Okay, so and when we convert to the plot contour, we can see that the experimental work for the overall hold up to the CFD prediction, the closest is 0.
1 minute.
Yeah?
You have 1 minute only.
Oh, 1 minute, okay. So the closest is for 0.125 meter per second. Okay, so this is where we plot the contour. We want to see which one is the best one. So 0.0125 is the heterogeneous region that we want in our case. Okay, so the conclusion show that the effect of population balance combined with breakup and coalescence model on the hydrodynamic has been considered, and the comparison with the D, and the experimental is significantly agree to the homogeneous regime. That's all from me. A very quick one, and thank you so much.
Thank you very much. It's a very interesting topic, at least for me.
Okay, so if anybody have questions, can contact me.
Do you have an? I think maybe I will in the near future I will contact you regarding this topic because I had some some efforts in the past in this area. Anyways, thank you very much for your contribution, Dr. Sethi, and we wish
thank you so much
in Jordan one day. So thank you, and see you. Bye bye. You can stop sharing the screen by your side.
Okay.
Thank you very much.
Thank you.